Okay. I am reviewing Lecture 5, which is Light and Quantum Theory. That is sections 3.1 and 3.3 in the textbook if you wanted to review it there. Okay, the first thing is light is a wave. It is made up of two oscillating fields, an oscillating electric field and an oscillating magnetic field, and they are perpendicular to each other. This is where we get the term electromagnetic radiation from those two fields. As you can see in this picture, the blue electric field is vertical and the magnetic field is red, and it oscillates in perpendicular and horizontal. There are a few terms we use to describe waves. The first is a crest, and it is the highest part of the wave. If you look at the picture, it's over here just at the top, and the opposite of that would be a trough, which is the lowest point over here on a wave. The amplitude is the maximum height of the wave, and we measure that from the midline up to the crest, or we could measure down to the trough too. And the next is wavelength, and that's the distance between two crests. And a node is a point on the wave where the amplitude is 0. Okay, wavelength, frequency, and speed are three things that are all related. Let's briefly talk about each one of these things relating to electromagnetic radiation. Wavelength, we use the symbol lambda, which is this upside down Y looking thing, and the units are meters. And like I said on the last slide, that's the distance from crest to crest or from trough to trough. Frequency uses the symbol nu, and its units are in 1/seconds or hertz, and it is the number of waves or cycles that pass in a second. Wavelength and frequency are inversely related. So that means as the wavelength increases, the frequency is going to decrease. The opposite is also true. When the wavelength gets smaller, the frequency is going to get higher. If we look at this picture, the wavelength that is more drawn out and longer can't have as many cycles in a second. And so this wave, the top wave is less frequent and the bottom wave is more frequent. All electromagnetic radiation travels at the speed of light. I'm using c for the speed of light, and it is equal to 2.998 times 10 to the 8th meters per second, and can be approximated using 3 times 10 to the 8th meters per second, which is very close. Okay, wavelength, frequency, and speed together gives us this equation. And that's c equals lambda nu. So the speed of light equals the wavelength times the frequency. And you can divide by that and solve for different ones to get the wavelength equals the speed of light over frequency, or frequency equals the speed of light over wavelength. And now I'm going to explain a practice problem. So the yellow light given off by a sodium vapor lamp used for public lighting has a wavelength of 589 nanometers. What is the frequency of this radiation? So we want frequency, which is nu, the symbol over here, and we want it alone, so we divide by both sides by the wavelength. So we get the frequency equals the speed of light over the wavelength. Okay, now we just plug in, so the frequency is equal to the speed of light, 2.998 times 10 to the 8th meters per second, over 589 times 10 to the 9th meters. Make sure you convert to nanometers, from nanometers to meters here, so our units match up. Nanometers is 10 to the -9th meters, so if we just multiply by that, we should be okay. And that is going to give us 5.09 times 10 to the 14th hertz, which is the frequency of the sodium vapor lamps. Okay. So all electromagnetic radiation exists along a spectrum called the electromagnetic spectrum. Remember that all electromagnetic radiation travels at the speed of light, but the wavelength and frequency determines which kind of electromagnetic radiation it is. On the left here are gamma rays with the highest energy, highest frequency, and lowest wavelength. On the opposite side is radio waves with the lowest energy, lowest frequency, and highest wavelength. The order of electromagnetic radiation on the spectrum is gamma rays, X-rays, ultraviolet, the visible spectrum, infrared, microwave, and radio, and that's something we probably all want to remember. And visible light is the small fraction of electromagnetic radiation that we can see, and it exists as color. It exists from 400 nanometers, which is violet, with the highest energy, to 750 nanometers, which is red with the lowest energy. We can remember it using the acronym ROY-G-BIV, which stands for red, orange, yellow, green, blue, indigo, and violet, as you probably know. Okay, one problem in the past with their understanding of classical physics was blackbody radiation. And a blackbody is a black object or gas that is a perfect absorber of light when it's cold. This just means that it absorbs all light. A blackbody becomes a perfect radiator of light when it is heated, and it emits all kinds of light. What spectra the blackbody emits depends on the temperature. A higher temperature is equivalent to higher energy waves, and remember that higher energy would be higher frequency and shorter wavelength. The understanding at this time was that the curve of a graph like this should not look like this. It is just instead keep going up. But as you can see, as the temperature gets higher, we're going to have higher and higher energy wavelengths, and we're going to increase on the electromagnetic spectrum. Okay, so Max Planck came up with a solution and proposed a few things that would explain black bodies. So he said a few things. So the first is energy is quantized. So energy is absorbed and emitted in discrete and specific quantities. And this means that energy is not emitted continuously. These packets of energy are called quanta. We can visualize the difference by looking at these two blue lines. This straight line is continuous, while this one is like steps, and you can only exist along the steps and not at any value. Planck also proposed that energy is proportional to frequency and came up with this equation here. So energy is equal to Planck's constant times the frequency. So the energy in this equation is in joules, and it represents a single quanta of energy. The joules in a single quanta of energy. H is Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds is the units on that. And that's going to be the same for any equation with H. And this is obviously frequency of the wave. So you can use this equation with our speed of light equals lambda nu equation. And when you solve for frequency, remember frequency is equal to the speed of light over wavelength. And you can get energy is equal to Planck's constant times the speed of light divided by a wavelength. And this equation relates a wavelength to energy. Okay. Another problem was classical physics couldn't explain the photoelectric effect. And Einstein is the person to remember with the photoelectric effect here. And the important thing about the photoelectric effect is that it was the first evidence for what Planck proposed about quanta, so small packets of energy. Okay, the photoelectric effect is when light of high enough energy shines on metal and emits electrons. These emitted electrons are called photoelectrons. And it only happens under certain conditions. The requirement for electrons to be emitted from the metal is that the frequency of the electromagnetic radiation hitting the metal has to meet a minimum frequency called the threshold frequency. And the symbol we use for this is the frequency symbol, so frequency and then not, so with 0 there. If the threshold frequency is not met, any intensity of light will not emit electrons. oh no, if the threshold frequency is met, any intensity will emit electrons. The intensity does not, as long as the threshold is met, electrons will be emitted. If it's not met, no electrons will be emitted. As the intensity increases, so if the intensity is above or below, it determines if it will emit electrons, but as the intensity increases, the number of electrons that are emitted will increase. If the frequency of the light is higher than the threshold frequency, that becomes kinetic energy of the emitted electrons. Okay, so we can see in this picture here, red light has the lowest frequency and it does not meet this metal's threshold frequency, so it does not emit any electrons. Green is a higher energy wave and has a higher frequency, and it looks like it is meeting the minimum threshold to emit electrons. The blue here is even higher, has an even higher frequency, and it'll emit more electrons, and the intensity, you can see, and if the intensity is greater, it will emit them. And the frequency is, okay, it can emit a lot of electrons, and they're coming off with more kinetic energy. So the important thing of Einstein's experiment and what he discovered with the photoelectric effect is light transfers energy in quanta called photons. So that means light is both a particle and now it's also a wave. It's a particle and a wave, and Einstein was the one that just proposed that it was a particle as well as a wave. Okay, this symbol here is the symbol for work function, this O with the I through it. And it is the minimum energy required to emit an electron from a surface. We use this equation here to calculate work function. So the work function is equal to Planck's constant times the threshold frequency. Work function, it is very related to the photoelectric effect because it is going to be how much energy the wave requires to emit an electron from a surface. So remember that we have to meet a threshold frequency, which is this symbol here. And this is in a graph to help picture what's going on. So these are using the physics symbols, so F for frequency and E sub K for kinetic energy. So if this is the threshold frequency here, if it is not met where the dotted line is here, no electrons will be emitted. As the threshold frequency is met, electrons will be emitted, that's right here, and as it increases, so that as the frequency increases above the threshold frequency, the kinetic energy will increase. So we can calculate this kinetic energy using a few different equations. So the first one from another lecture, we know that the kinetic energy of an electron is equal to half times the mass times the velocity, or speed squared. Okay, and that is equal to the energy minus the work function. So if the kinetic energy of the electron is equal to energy minus the work function, remember that energy equals Planck's constant times the frequency, and that's here, and then work function, and then we can, if we take that, remember that from right here, work function equals Planck's constant times the threshold frequency, so we can get this final equation that kinetic energy of the electron is equal to Planck's constant times the frequency minus Planck's constant times the threshold frequency. And remember that if the electron has the kinetic energy, electron has more kinetic energy as the frequency of the incident radiation is above. It gets higher and higher above the threshold frequency. Okay, so now we're going to do a practice problem with work function and energy. So a photon with a frequency of 5.00 times 10 to the 14th hertz, so that's the frequency, strikes a photoemissive surface whose work function is 2.60 times 10 to the negative 19th joules. So we're going to calculate the energy of the incoming photon, the maximum kinetic energy of the ejected photoelectron, and the threshold frequency. So on this first part, part A, the energy of the incoming photon, we're calculating energy of a photon. And remember, we're going to use the equation E equals Planck's constant times frequency equals hv, or h nu. And so we're just going to, remember, energy is the energy in joules of quanta of energy, or photon too. Okay, so our energy is going to be equal to Planck's constant here, 6.626 times 10 to the negative 34th joule seconds. And we're going to multiply that by the frequency, which is 5.00 times 10 to the 14th hertz. And we're going to get our answer here, 3.31 times 10 to the negative 19th joules. And now it would be three significant figures because in our frequency is three significant figures, and we can go farther on Planck's constant. Okay, and that's in joules. Part B is the maximum kinetic energy of the ejected photoelectron. Okay, we're going to use one of those equations from the previous slide for kinetic energy of the electron. And we have work function, and so we're going to use the one with work function in it. So the kinetic energy of the electron equals Planck's constant times the frequency minus the work function. Okay, so we just sub in what we know there, and the kinetic energy is, so we already calculated this. You could put Planck's constant frequency in again, but it is this 3.31 times 10 to the negative 19 joules already. So if we put that in there and then subtract the work function, 2.60 times 10 to the negative 19 joules, we're going to get our answer here, 7.13 times 10 to the negative 20th joules. Okay, and our third question is the threshold frequency. And we need to calculate it. So we need to relate it to an equation with the threshold frequency, and the best one to use is the work function equals Planck's constant times the threshold frequency, because we have the work function and that's just a constant. So we solve our equation for the threshold frequency, and just dividing by Planck's constant, we get the threshold frequency equals the work function divided by Planck's constant. So we just plug our numbers in here. The work function is 2.60 times 10 to the negative 19 joules, and we divide it by Planck's constant, 6.626 times 10 to the negative 34th joule seconds, and we're going to get our answer here, which is 3.92 times, oh, sorry, that's a typo there, 3.92 times 10 to the 14th hertz. It should not have another one there. Okay. And the last thing we're going to review is just the equations, because there are a lot in this lecture and this topic. So our first one, and that we went over first, relates speed, wavelength, and frequency for the equation C equals lambda times nu, which is speed of light equals wavelength times frequency. And remember, you can solve for wavelength, you can solve for frequency, which is going to be really helpful with a lot of equations. Remember, C is a constant in electromagnetic radiation because they all travel at the speed of light, which is 2.998 times 10 to the 8th meters per second. The next equation we're going to review is E equals h nu. So energy equals Planck's constant times the frequency. And like I said, relates energy and frequency. Remember that H is Planck's constant, 6.626 times 10 to the negative 34th joule seconds. And this second equation here equals Planck's constant times the speed of light divided by wavelength is found by using this first equation and first equation solved for frequency and just replacing the frequency with the speed of light over the wavelength. And that is going to relate energy and wavelength and can save you time from doing multiple steps in the equation. Okay, this next equation is for work function, and work function equals Planck's constant times the threshold frequency. And like I said, this relates work function and threshold frequency. Remember, H is Planck's constant, which is over here. The next equations are the kinetic energy of electron equations, and this is for the photoelectric effect. The kinetic energy is always equal to half times mass times velocity squared, and so is the kinetic energy of electron. And it is equal to the energy minus the work function. If we sub in other equations here, remember energy equals hv, and that's where that's from, and that work function equals h, and the well, okay, energy equals Planck's constant times frequency, which is where we got that, and work function equals Planck's constant times threshold frequency, which is where we got that. So relates kinetic energy, and then energy and work function. And like I said, using other equations, we can relate kinetic energy to frequency and threshold frequency. Okay, that is all I have for this lecture to review. I think the most important things to remember are all the equations, be able to understand them and be able to use them in problems, and also understand the problem that of blackbody radiation and what the photoelectric effect is, and how to, and then just I do a lot of practice problems. And that is all.